Hello students, welcome back. This is assessment problem 3.2, which is a very interesting problem, and this problem basically illustrates the concept of the loading effect. Here we have a very simple series circuit in which across the 7 kilo ohm resistor a load resistor is connected. So what is it asking us to find the no load value of V naught in the circuit shown. When there is no load here, it means RL is equal to infinity, or it is open circuit. So the RL is not available here, therefore the voltage V naught is all dissipated across 7 kilo ohm, because it is not available here. So now this is a simple series circuit. So in this series circuit we have of the form, now we have 25 kilo ohm, this is 75 kilo ohm, and this is a voltage source of 200 volts. So now to find out the voltage here, which is V naught, which we will use a voltage divider law. So according to the voltage divider law, this is 75k, 25k plus 75k multiplied by the total voltage, which is 200 volts. So V naught here is basically the 150 volts. So this is the value of the V naught when load voltage when load resistance is not available. So this is the actual voltage without any dissipation. Okay, this is our voltage. So now for the other part, find V naught when RL is 150 kilo. So when the value of RL is 150 kilo, when this is 150 kilo, so now we can see that these two resistors are in parallel with each other. So for part B, when these two resistors are in parallel with each other, we have to find out the equivalent resistance of these two resistors, which is 75k multiplied by 150k divided by the 75k plus 150k. So calculating this value, we will get a resistance of 50k. So we can also see here that initially it was 75k. By connecting a resistance of very high resistance, this is 150k is a very high resistance, I mean it is double than this already available resistance. So this is a very high resistance, but by connecting it we can also see the sudden decrease in the available resistance. So when the resistance is decreased, we will also see that the voltage dissipation across this resistance will also decrease. So this is basically the loading effect. Okay, so how is it decreased? How much power dissipates it in the 5 kilo ohm resistor if the load terminal accidentally shorted? Okay, so now we have to find out the V naught when this 50k is the equivalent resistance. So now the value of V naught is now 50k divided by this resistance 25k plus the equivalent resistance now multiplied by the total voltage here. So by calculating it, we find out that the voltage is dropped to the 133.3 volts. So you can see that initially the original voltage was 150 volts. It is now decreased to 133.3 volts by attaching a very high resistance of 150k. So this is a loading effect. If you have designed a circuit and you are connecting any resistor or load with that circuit, so its resistance will decrease, equivalent resistance will decrease, which will ultimately result in the decrease in the voltage dissipation across that resistor or that load, which will certainly affect the performance of that resistor. So you have to keep these things in mind, and this is also called the loading effect. So for solving the question like this one, the ultimate aim was to let you guys know about the loading effect. So now this is this one. How much power dissipated in the 25 kilo ohm resistor if the load terminals are accidentally shorted? When the load terminals are shorted, so it means RL is 0 when these two are connected in such a way that this terminal is shorted, so all the current will come here and it will follow this route. Okay, the current is coming here and it will follow this route, because now it is the current is following a path which has the lowest resistance, so it will follow this one. So now the circuit we will have will composed of a single source and a single resistor. So the overall voltage will be dissipated across this 25 kilo ohm. So now the power dissipation across this one will be equal to V square divided by R. V is 200, which is all dissipated across this 25 kilo ohm, and its resistance is 25k. So the power dissipation will be equal to 1.6 watt. So this is the solution of part C. What is the maximum power dissipated in the 75 kilo ohm resistor? So the maximum power, it is also a very conceptual statement, because the maximum power will dissipate across this 65 kilo ohm when maximum current will flow through this resistor, and it will only be possible when RL is infinity. There will be no current here, all current will pass through here, and it will be the scenario like which was encountered in part A. So by using the same scenario here, we will find out the maximum power dissipation, which is now 150 whole square divided by the 75k. So the maximum power dissipation here will be 0.3 watts. So this is the maximum power dissipation when the value of RL will be infinity, so maximum current will flow through this resistor. So this is also a very interesting question, which basically described the effect of loading by connecting another load in the design circuit. The all the effects which we can encounter in a circuit are described here. So I think you will grasp these concepts very firmly and will use it in your design process. Thank you so much, and I'll see you in the next lecture.